Thank you for joining our online data science meetup at ING. The topic of this second talk today is about multi-level classification, which is a topic I'm familiar with because of my PhD. And actually, I would like to thank my supervisor, Professor Pedro Larrañaga, for sharing some of the material I'll present today. So today we will introduce to multi-level classification. We will see what kind of algorithms we can find in the literature that allow us to solve multi-level classification. And also we will review some software and data sets so that you all can start your own learning path and keep practicing with this multi-level paradigm. And this is the main goal, that you all acquire new knowledge, but also consolidate it. So after the 20 minutes of this presentation, we'll have a 10-minute session of question and answer. So please feel free to share your questions in the chat, and I'll be glad to answer all of them at the end. Okay, so let's start with some overview and basics of what kind of algorithms we can find in the literature and what really multi-level means. Here you have a comparison between a classification problem that involves single label data at the top of the screen and multi-level data at the bottom. You can see that we all are used to work with this single label case in which we have just one single class variable to be predicted based on the values of some feature variables x1, x2, x3, etc. Here we could measure the correlations between the features and the class variable to finally search for the best classification model, for example, which could be a random forest, logistic regression, neural network, etc. In multi-level classification, instead, we have multiple class variables to be predicted at the same time, which in addition usually present correlations between them and not only with the feature variables. You can see that traditional machine learning algorithms, those we just named, cannot deal with this kind of problems with multiple class variables at the same time. So we will see in the coming slides what kind of algorithms are proposed in the literature. Okay, one more comment in this slide I'd like to make clear. I've taken this graph here in the top right corner from a publication has been accepted in the Artificial Intelligence Review journal. You can see the relationships between the different paradigms of classification. So for example, binary classification would be this example in the left, when we have one class variable to be predicted with two possible values. Multi-class, I'm sure you'll have heard it as well, is when we have, again, only one class variable to be predicted, but with multiple possible values. Both binary and multi-class can be referred to as one-dimensional classification, since only one class variable is to be predicted. Multi-level classification is this example below in this slide, such that we have multiple class variables and all of them being binary with two possible values. Each class variable is seen as a label, that's why the name of multi-level classification, and each label can be present or absent with a value of 1 and 0 respectively. Multidimensional classification is a more general classification problem, and you can think in it as a combination of multi-class and multi-label problems, because it involves multiple class variables with multiple possible values for each of them. So today we will focus on multi-level classification, which is a simpler version of multidimensional classification, but it is much more popular. So multi-level classification problems come about in numerous application domains, and it has been a hot topic in machine learning literature during recent years. For example, in terms of image understanding, we all know the popular binary classification problem about classifying an image as a cat or not a cat. From the multi-level perspective, we can enrich this problem by predicting the presence or absence of more than one object. This is having multiple values in labels, instead of just one. For example, here in this example, the label grass is present in the 3 images, but the label cow is only present in the first one. This is a good example also for you to show that correlations between labels are common in multi-label problems. For example, if the label airplane is present, as it's happening in the 3rd image, I can think that the label sky will also be present with high probability. More examples of applications are shown here, such as demographic classification, And you will find many more in the literature since, as I say, multi-level classification is a very popular topic during recent years. A bit more of basics. You may find multi-level classification with 3 different notations, but all of them meaning a similar thing. The first one, regarding class variables, is the one we all are familiar with. Here, multi-level classification is about finding a function h that assigns a vector of d class values to each vector of m feature variables. And this is each class variable c sub 1, c sub 2, etc. is predicted with a value. Here in multi-level with a 1 or with a 0, since a label can only be present or absent. The labels notation, this second one, assigns a subset of present labels to the vector of feature values. This is those that have a 1 from the class variables notation are the labels that are assigned to the vector of features. As you can see, the meaning of both notations is the same, but just wanted to mention it for you to know that you can find different ways of defining a multi-level classification problem in the literature. Okay, and there is a third notation, the ranking one, which is slightly different. Here, the output of the classification problem is a ranking among the labels. We have that the present labels from the other notations will have the highest ranks in the ranking, and the absent labels will have the last positions in the ranking. For example, for this first data case, a possible ranking could be first the label 1, since it's present, second the label 4, because it's again present, third the label 2, because it's absent for that example, and fourth the label 3. Some of you will have already realized that assessing the performance of a multi-label classifier needs a different approach to that from the single label case. Here in multi-level classification, we are predicting multiple values at the same time, so measuring how well we are doing should consider the performance of all the class variables predictions and not just a single one. You can find multiple evaluation metrics in the literature. Here, I'm just sharing a compilation I made for both multi-level and multidimensional problems. You can see we have some metrics when our prediction is a hard classification. This is when the labels are present or absent. We are just giving a 1 or a 0. We also have metrics when our prediction is a probabilistic classification. This is how probable is each label to be present or absent. And finally, other metrics when our prediction is a ranking among the labels. This third notation we just saw in the previous slide. Without going into too much detail, let's just see the 2 most used metrics in the literature. The 0-1 subset accuracy can be seen as an extension of the traditional accuracy. It's going to have a value of 1 when an example is correctly classified in all labels, and a 0 when not, no matter if just a single label was misclassified. The Hamming loss, instead, is much less strict, since it measures how many labels are being misclassified. Of course, there are more complex metrics available in the literature, but yeah, just wanted to show the 2 most used. And let's move on to the core of the presentation, to the algorithms that allow to perform multi-level classification. Tsumakas in 2009 categorized the algorithms in 2 groups: problem transformation on the left and algorithm adaptation on the right, you can see. Since these 2 types of algorithms address the classification in a different way. The problem transformation, on the one hand, transform the multi-level classification problem into 1 or more single-level classification problems, and each of these sub-problems are solved with traditional models, such as random forest, Bayesian networks, whatever you want to learn there. The algorithm adaptation methods, instead, extend a specific classification algorithm to directly deal with multi-level data. I let you hear some references to specific single-level classifiers that were extended to multi-level classification. And you can see they were published in really well-known journals and conferences. Today, we will focus on the first group, the problem transformation methods. Since these algorithms have a common thread and it results easier for you to get an overview, Nevertheless, I'll also present the extension of Bayesian networks as an example of algorithm adaptation. So let's go then with the problem transformation methods. The first one, it's called binary relevance, is the simplest method. Basically, it just transforms the multi-label problem into as many single label problems as labels. For each of the labels, it's going to learn one binary classifier independently of the rest of the labels. Then the relationships between labels are not going to be considered. As I said, this is the simplest method, so let's see how we can improve it. This algorithm, called ranking by pairwise comparison, learns a binary classifier for each pair of labels. This is label 1 versus label 2, 1 versus 3, 1 versus 4, 2 versus 3, etc. Each model is going to predict which label of the two is preferred. Then each model is trained with examples that have present one of the labels, but not both. For example, this first model is trained with examples that have label 1, this is x1 and x3, and those that have label 2, this is x4, but not both of them. And for example, x5 is excluded since both labels are equally preferred, and it's giving no information to this particular model. Okay, so at the end, each model is going to give a vote to any of the two labels, the one that is preferred, and the votes of all models are summed, such that we have a ranking of preference between the labels, as you can see here in the bottom of the slide. In this example, the label 3 received all possible votes and has the highest rank, and the label 2 instead didn't receive any vote and occupies the last position in the ranking. As you can see, no hard classification is achieved, but yeah, there are some techniques in the literature that allow you to threshold this ranking and have a final bipartition of the ranking into present and absent labels, into positive and negative labels. Okay, the next method does perform a hard classification. We are going to know which labels are present for any of the examples. It's called calibrated label ranking, and it is a combination of the previous two. It's going to learn both those models from binary relevance on the top, as many as labels, and those from the ranking by pairwise comparison method on the second row, as many as pairs of labels. Again, each model is giving a vote to one of the two labels. For binary relevance models, although we only have one label to give a vote, it's like we are adding a virtual label, lambda sub 0, which is going to be later used as a splitting point between present labels and absent labels. So at the end, we have again a ranking among the labels and also a hard classification, as I told you. For example, label 3 and label 1 score higher than the virtual label, and that's why they are the ones that are finally classified as positive labels. In addition, we know that the label 3 was preferred to label 1 in case that we just want to give the most preferred label. Okay, let's move to the next classifier. It's called classifier chains, and its extended version, ensembles of classifier chains. This method learns again as many binary models as labels, and each model is going to predict the present of each label. The trick here is that this learning process is done as it was a chain, such that the predictions from previous models are taken as extra feature variables for the next models in the chain. Then relationships between labels are somehow taken into account. However, you can think that this method is dependent to the order of the chain you choose, and you may obtain different results with different orders of the class variables in the chain. And also, models that are placed at the end of the chain may result in less accurate predictions because you are concatenating this error in the predictions of the previous models. That's why an ensemble version of this method was also proposed, which uses several orders of the chain, and at the end, the predictions are averaged of all the models in the ensemble. Okay, Labourpower set is a really naive method, again, like the Labourpower set, like the binary relevance one, sorry. And actually, they both are considered the simplest ones that give rise to smarter multi-label classifiers. Here in Labourpower set, each possible combination of present and absence of labels is annotated as a different class value in a new multi-class classification problem. Then we have all possible values, which are 000, 001, 010, 011, etc. It has, as you can imagine, two main drawbacks. The complexity is exponential in the number of labels, as it will have too many class values, which in addition, extremely few training examples for some of them. And also, this method is unable to predict label configurations that do not appear in the set of model that was trained with. For example, in this example, if the combination 1111 is not available in the training set, then this method won't be able to give a prediction of this value. So there are some models that try to improve the limitations of this Labourpower set. The first one is the Prune sets and its ensemble version again. Here, those label sets, this label set is a combination of labels that rarely occur are Prune, and they are reintroduced along with subset of the label sets. In this example, the label sets of labels 3 and 4 is Prune, since only 2 total cases exist in the dataset. At the same time, those cases are reintroduced in the dataset along with label sets of label 4, this fourth example in the training set. Instead, the label set of labels 2 and 3, this third one, is not a subset of label 3 and label 4 because label 2 is not included in the original label set. So thanks to this method, we have reduced the complexity of Labourpower set, since not all possible combinations are to be predicted, but we still are unable to generalize to configurations not appearing in the training set. By using, again, an ensemble version of this model, we can avoid this limitation of generalizing to unseen combination of label sets. An ensemble of Prune sets is going to create as many data sets as models to be part of the ensemble by using sampling techniques. For example, bootstrap, let's say. For each sample data set, a Prune set model is going to be learned. Then each Prune set model predicts the most probable label set, then giving a vote to the labels present in this label set that it's predicting. Again, the votes are summed for all the models, and a ranking of presence among the labels is achieved. If we want to pass to a hard classification, we just have to apply a thresholding method, and we will know which labels are present, are positive, and which ones are absent. We have another algorithm that it's called random k-level set, also Rakel in the literature. While the ensemble of Prune sets we have just seen selects the label sets with sampling techniques, this Rakel method selects them at random. Then it's going to create n models. In this example, n is equal to 6 to solve simple subproblems of label sets of size k. In this example, k is equal to 3. Each model is a Labourpower set, the one that models all possible label combinations 0001 that we just saw in 2 slides ago. And now the number of labels of these subproblems that Labourpower set is modeling is highly reduced. That's why Labourpower set now does make sense. Again, each model of the ensemble is going to predict the most probable label set, of course, only of those labels that the model works with. For example, this first model H1 is only going to predict if label 1, label 2, and label 8 are present or absent. In this example, only label 1 and label 8 were present, so both of them are going to receive a vote. And the votes are going to be summed along all the models. We have, again, a ranking of present, of popularity between the labels. And if we want to apply a threshold value, we can have which of those labels at the top of the ranking are actually present. As you would expect, the greater the number of votes per label is, the higher the effectiveness of the Rakel method. The number of models n and the size of the label sets k are proportional to the number of expected votes per label. At the same time, we don't want them to be too big. Otherwise, the complexity of graphical method will increase. It's suggested in the literature to use key equal to 3 and n equals to twice the number of labels in order to have 6 expected votes for each label. Okay, the models we have reviewed are the most frequent ones that you can find in the literature. If you start browsing the literature, you will find many more multi-level classifiers. For example, this one called Homer that converts the multi-level problem in a smaller subproblems in a hierarchical way. Okay, let's move on to the second block of group of algorithms, which are the algorithm adaptation. Here we are going to be quicker. This is the multidimensional Bayesian network classifier, or MBC in short, which extends traditional Bayesian network classifiers to directly deal with multi-label data. Those that are familiar with Bayesian networks will know that this model encodes the conditional independencies between triplets of variables in this directed acyclic graph structure. Without going into too much detail, the change here in the multi-level paradigm is that we are creating as many nodes in the Bayesian network as class variables we want to predict, instead of just one node as it happens in the single label case. Then we can distinguish these three different subgraphs of the MBC. The class subgraph is going to model the dependencies between the class variables. The breadth subgraph represents dependencies between class and feature variables. And the feature subgraph models, models dependencies between the features of our problem. Also, this last slide, this is an extension of MBC's classifiers. This is a paper I published 2 years ago. Basically, you can see that this method places general MBCs in the leaf nodes of a classification tree, and an internal node is a feature variable that has as many children nodes as the possible values of the associated feature. And new samples are going to be classified with the corresponding MBC leaf in relation to the values of the feature variables that make up the internal nodes. Okay, almost the end. I wanted now to share with you some data and software you can find in the literature so that you all can start playing with them and consolidating the information we have been presented today. In this link, in Cometa UGiant.s datasets, you will find a lot of benchmark datasets with different size in terms of data, in terms of number of features and number of labels. And actually, some of these datasets are used in the literature for comparing different multi-level classifiers and those that you are proposing as new in the literature. Regarding software, you have available libraries in R, Python, Java, and I think there is also one in MATLAB. The Python library is a scikit base, which is really nice. The one I've used most is the R one, which is very complete. You can see that we are talking about recent work, 2018, 2019. And should you want to explore a bit more the literature, I recommend you these two nice up-to-date papers, which reflect they are two reviews that basically show the most important information of multi-level data. And just to finish, some code from the R library, just for you to see that what we have presented today is what you can find in the literature. Sorry. For example, here in this slide, we are reading a multi-level dataset called birds, with the goal of predicting what birds are singing based on some acoustic features. Each bird is then a label, which is going to be present if the given bird is singing and absent if it's not. As you can see here, just with this call that is circled in orange and blue, we are learning a binary relevance multi-level algorithm with a random forest as base classifier. This library offers many multi-level classifiers, not only this one. For example, all those we have seen today are available in this library. You can see here binary relevance, ranking by pairwise comparison. I'm following the order here. Calibrated label ranking, classifier chains, ensemble of classifier chains, Labourpower set, Prune sets, ensemble of Prune sets, Rakel, and Homer. All those we have seen today. Also, different base classifiers are available. for example, random forest, naive Bayes, support vector machine, but also random majority-based classifiers predict respectively random values and the majority value of all labels, which is really helpful if we want to compare our best algorithm after tuning it with these naive models that they should work worse than our tuned algorithm. So we have reached the end of the presentation. Hope you have enjoyed it, and also hope you can start browsing the literature. You'll see there are many papers with many sites, since multi-level has been a hot topic in machine learning during recent years. And hope you can start identifying multi-level problems in your business and giving them a solution based on data. So thanks for your attention. It has been a pleasure. Yeah, it's time for some questions now.
Thank you, Santiago. You did excellent. There were some people who were asking us if we can share your presentation later, which I do believe we can. If people will give us their email address, then I will forward your presentation, also the presentation of Daniel, and also the next presentation that we will present. I see we do have a question from Dan, who is saying, is the R implementation more sophisticated than Python?
So we have 4 possible programming languages, which are Python, R, Java, and MATLAB. I think MATLAB, you are not going to be interested in it. Yeah, I would recommend you the Python one or the R one.
Okay. Thank you, Santiago. And the next question is, what's the SOTA in multi-label classification for tabular data?
So thank you, Manuel, for the question. For tabular data, the state of the art, I would say that Rakel, the random k-level sets classifier, is the one that performs the best, or in general the best. But yeah, as you know, in machine learning, there is a theorem, the no freelance theorem, that says that no single learning algorithm is going to perform the best one in all possible types of data sets. So yeah, what I can suggest you is you just to learn all the models, just tune them, and let's see which one is performing the best one for your specific data.
Thank you, Santiago. Another question from Francisco Javier, who is asking, what do you think is the most successful algo in multi-level problems?
Okay, so the same question again. I would suggest you Rakel. It's the one that it's giving me the best results so far, but it really depends on your data. So I would suggest you to train all the models that are available in these libraries, making hyperparameter tuning, and yeah, you will be able to find the algorithm that best works for you.
Okay, great. Thank you. So if there